Let's have a look at question 37 in this video. So, for professors, a large variance in the final marks indicates that the exam was successful in identifying good students. Now we have two class sizes of 26 and 29 respectively, and the sample variances, so the sample variances were 6 and 3.2 respectively for the two groups. Now we're testing whether the population variances differ, and we assume that the grades follow a normal distribution. So what do we conclude based on that? At a significance level of 0.10. Now what's the intuition here? We have two variances. We have a larger sample variance and a smaller sample variance. It's 6 and 3.2. So let's write that here. We have a larger sample variance of 6 and we have a smaller sample variance of 3.2. Now in statistics, as always, the sample data is an estimate of the population data because we cannot test in the entire population, so we're taking a random sample and we're estimating the population parameters, and in this case the sample variance is an estimate of the population variance, and the other one is also an estimate of the population variance for the second group. So that's the first group, that's the second group. What we're testing is if there's a difference in the population variances. So our null hypothesis is that the variances are equal. So under the null hypothesis we always assume that there's no significant difference, but under the alternative hypothesis we infer that there is a significant difference and we want to test that. So as we said, because we're estimating with sample data, we're also testing with the sample data. We're using the sample data, the sample variances, to perform our test. And to make a test on variances, we do an F-test. We're performing an F-test, which looks at the ratio between the larger variance and the smaller variance. And the intuition is that if the variances are similar to each other, if they are, if the ratio between them is very close to 1, so if the ratio between them is close to 1, it means that the larger variance is approximately equal to the smaller variance. If the F-test has a ratio of approximately 1. In that case, we would not have any reason to believe that they differ. But if that's not the case, if the ratio between them is significantly higher than 1, then we have enough evidence that the larger variance is significantly higher than the smaller variance. So that would mean that the population variances differ. So let's do so and we'll see if that's true or not. What's the larger variance here? We saw that that's equal to 6. So the F value that we're calculating, the F statistic, is going to be equal to 6 divided by 3.2, and that's going to equal to 1.875. Now, just like with any other test, we have to compare our F value with the F critical value. So we're going to compare it with the critical value F at a significance level of 10%, but because we have a two-sided test, we're going to divide the 10% by 2. So we will have F critical value at the 10% level divided by 2. Now in the degrees of freedom, I'd like to stress that we have to pay attention. We have 1 degree of freedom in the numerator, which is the number of the larger sample variance, the number of observations of the sample with the larger variance, minus 1, and in the denominator we have the number of observations in the sample with the smaller variance, minus 1. And the thing I'm trying to stress here is that this is not the number of observations that is larger, it's the number of observations in the sample with the larger variance. And I hope this makes the difference, this stresses the difference. So pay attention to that because that's a common mistake to make. Now, we have the F critical value, 10% divided by 2, that's going to give us 5%, that's what we're going to check in the table. And the number of observations of the larger variance, we can check it over here. We have that the sizes are 26 and 29, so for the variances of 6 and 3.2 respectively, meaning that the first variance has a number of observations of 6 and the second variance has a number of observations of 29, and this one of 26. So 26 for the first variance, 29 for the second variance. And notice what's happening here. The number of observations of the larger variance is 26, which is smaller than the number of observations of the smaller sample variance, which is 29. So we will put that into our degrees of freedom. We will have 26 minus 2 26 minus 1, and here we have 29 minus 1. So the F critical value will have the degrees of freedom. F critical value at 5% will have the degrees of freedom of 25 and 28 respectively. Now if we check this in our table, we will have a critical value of 1.91. So let's plot this data on our F distribution and we'll see whether we reject the hypothesis or not. If we have here our F distribution and we have the critical value of 1.91, this is going to be our critical value of 1.91 where we reject the hypothesis, and then our actual value that we found with the F test is 1.875, and if we plot it over here, that's going to be to the left of the rejection region. So 1.875, we can see that it's not in the rejection region, so we do not reject the null hypothesis, meaning that the variances don't differ significantly. So the variances don't differ significantly, and intuitively it makes sense by looking at the F value that we found. 1.875 is not that much higher than 1, so the ratio between the variances is also not that high, meaning that the larger variance is not significantly higher than the smaller variance to claim that there is a difference in the population variance. So if we have a look at the answer key, using a significance level of 10%, the professor concludes that the variances differ, and that is false. We saw that we do not have enough evidence to say that the variances differ. Hope this makes sense, and we are done.